The broadcast is now starting. All attendees are in listen-only mode.
Hey everybody, welcome back to Amazing Mechatronics and Young Engineers of Today. We're going to continue with Arduino today to nobody's surprise, but we're going to finish off our multi-LED monstrosity, all that code and everything like that. So just as a bit of a refresher, I'm going to go to tinkercad.com so that we can pull up our project. Let me see, I'm not signed in, so let me go ahead and do that. And if we go to circuits, here it is. This is our 8 LED project. I believe the code is still in the code editor. Yes, it is. So this is what we did the last time around, and I had a whole lot of typing involved because we painstakingly listed every LED variable, and then we set it up individually for each of these. So LED pin 1 high, delay 1000, LED pin 1 low, delay 1000, LED pin 2 high, delay 1000, LED pin 2 low, delay 1000, so on and so forth, from LED pin 1 to LED pin 8, because we had 8 LED pins hooked up, which was a huge pain. And then I talked about the beginnings of something called an array, which is basically just a collection of variables all sort of crammed together into one location. In fact, if we wanted to think about it literally, they are pretty much in one location. They're all right next to each other in memory, so that we can easily keep track of all these related values. But it didn't really seem to make things a lot easier. See, we've got one line of code now that keeps track of all of our LED pins. However, we still have just as many lines of code down here for turning them off and on and setting them up to be outputs and stuff like that, because there is a second part that I was talking about that would really go towards making this code a lot more streamlined, that could leverage the power of arrays as well as another thing, and would make our lives a lot easier. But I didn't really get any time to go over it. But first, a little bit of a review for arrays. Like I said, they're all in the same place in the code, so we can reference all of them. They work just like regular variables, so we could change individual values on these if we wanted to. We could change this 4 to a 7 or something like that. We don't really want to, so we're going to keep it a 4, but we could totally do that. We could change it in the code as well. We could change the value of this 4 by referencing it in the code. And that's exactly what these numbers in square brackets are. These numbers in square brackets refer to individual positions. 0 refers to the first position, 1 refers to the second position, 2 refers to the third position, and so on and so forth, all the way up to whatever, if the size of the array is said to be n, that is to say this has 8 values, so this array is size 8, then n minus 1 will reference the last value of that array, in this case 7. The reason why that is because we start counting at 0 with arrays. The reason why that is sort of lost to the mists of time, but a lot of people like to say it's because when arrays were first created, memory was much more the word I'm looking for is not sparse, but there was less of it, and so you had to be much more frugal with your memory. And so somebody at one point said, "Hey, so if we ignore 0, we're ignoring this perfectly good number that we could be using for counting and holding information and stuff like that. So why are we doing that? And we need to do extra, math to it in order to increment it by 1 so that they know and everything." So they said, "Hey, we'll just have it start counting at 0 so that you can use the entire length of the array, as well as not having to do any additional math or anything like that." And thus the 0 indexed array was born, I guess. And a lot of other things just sort of start at 0 as well, because the languages that they're based off of also start at 0. It's a lot of sort of habit passed down from generation to generation at this point. There's no real huge reason to have it start at 0. That being said, for me, it's very comfortable, so I'm okay with it staying at 0. I don't really care. Um, but there are people out there who have opinions about this sort of matter, and they say that it should start at 1 because we as humans start counting at 1. And there are other people who say, well, computers start at 0, so we should have it start at 0, and whatever. I try and stay out of that kind of stuff. Anyway, that's neither here nor there. The important thing to remember is many, 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 many arrays in many, 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 many languages. I should say arrays in many, many, many languages, because all arrays in a given language will start at either 0 or 1, but many languages have their arrays start at 0, so that's an important thing to keep track of. Conversely, because they start at 0, if I tried to access LED pins 8, nothing would happen. In fact, the computer would probably freak out at me, even though there are 8 elements. And that's because we start at 0. So you end at however large it is, minus 1. Anyway, I promised you that super sweet expansion upon concepts, which would allow you to make this a lot smaller. Now, this concept is very useful because you'll notice that there are a lot of repeated lines of code here, like a whole lot of repetition. And we could cut down on this repetition, excuse me, because even though there's one character that's different between each of these lines. And we set it up so that that character is interchangeable. More on that in a moment. But a lot of this is repeated code. And there is a framework in place in pretty much all programming languages that allows you to run repeated code or run a bit of code over and over again so you don't have to repeat the code like we're doing here. And that is the loop. The loop is wonderful. The loop allows you to do all sorts of stuff. Let me pull up my paint. The loop allows you to repeat all kinds of code. A loop, basically, all it does is it says, hey, so everything inside my loopy here, I don't know why I used a cursive L there, but everything inside my loop here will get repeated over and over again for as long as I say. This is an I. Repeat I times. I being some number of times. It can be anywhere from 0 to infinity. So we can have it run 0 times, we can have it run 1 time, we can have it run 10 times, we can have it run 1,000,000 times, we can have it run forever and ever and ever until we somehow force the program to quit or cut the power to the computer. I wonder if that sounds familiar, like maybe the void loop over here or something like that. So I know it's probably not really that groundbreaking of a concept considering we have a function called void loop here, but there are loops that you can create of your own that are more controlled than just the void loop. In fact, let's touch on the first one that we're gonna use, which is called the for loop. The for loop is so named because, well, that's the keyword you use in order to initialize the loop, but a lot of these are named because of the sort of the grammar that goes through your head when you're describing it, because they have roots in mathematics. And mathematics has a similar sort of structure to it. You might say, for any given number I, let's say for a number I that is equal to 0, as long as I is less than this value, this statement is true. And it's got math roots. So they kind of translated that over to programming. And so you have the for loop, which is the sort of the easiest of the loops to control. Because it can be the easiest one to sort of visualize and figure out what's going on. Now, it may not look the nicest out of all of the loops, but it's certainly the easiest one to wrap your head around. So we could say for, and then we've got the initial condition, and then we've got the, this is a semicolon, by the way, not a J. So we got the initial condition. Let's turn this into more of a semicolon. Boop, boop, boop. And then we've got the truth, the checker. Let's instead of truth, let's say the checker. So we got the initial, we've got the check, and then we've got some math. And then the for loop starts in earnest. So what do I mean by this? Initialize, check, and math. All right, let's expand upon it. So we might say for int I is equal to maybe 0, as long as I is less than 8, and then I equals I plus 1. Code. So what exactly is happening here? Okay, well, we've got our initializer, we've got our check, and we've got our math. And I know I'm spending a lot of time on this, but this is a really big concept for programming loops, and specifically the for loop. So I want to spend as much time as possible going over this until it makes sense to you guys. Actually, before I continue, show of hands, who's already familiar with for loops? Okay, so we got a couple of hands, but we're looking at less than half the class. So I'm going to go ahead and run through this just so we're everybody's on the same page, because that's one of those things that like you really want to be certain of. So we've got the initializer, we got the check, and we got the math. The initializer determines the starting conditions. So in this case, for our loop, we're going to have a variable that keeps track of how many times the loop has run. In this case, the variable is I. And we're saying I is an integer and is equal to 0. So this is our starting condition. I is our variable keeping track of how many times the loop is run, and it is 0. We're starting at 0. Next, we have the check. So I is our variable that keeps track of how long it's running. As long as I is less than 8, keep running the loop. So every time this loop runs through once, it's going to go back up to the top and it's going to check, hey, is I less than 8? If it is, we're cool. Keep going. As soon as I is no longer less than 8, so that could mean that I is equal to 8, or I is greater than 8, although in this case, we shouldn't run into that situation. But if it's either of these conditions, this one is no longer true, and then the loop stops. We immediately dump to the next bit of code that's after the loop. We just dump the loop out of memory and we continue on. Well, not really out of memory, but we stop running the loop when we move to whatever's after the loop. So this is our check. As long as this is true, we continue the loop. Then we've got our math. In this case, I equals I plus 1. So every time the loop runs, we take I and we add 1 to it. That's all this means. This just means that we add 1 to I every time the loop runs through. So the first time the loop runs through, I is at 0. Next time it's at 1, then it's at 2, then it's at 3, then it's at 4, then it's at 5, then it's at 6, then it's at 7, then it's at 8. And then we come back up to the top to check, and we go, hey, I is equal to 8. That's not less than 8. It's equal to 8. Don't run the loop. It's no longer true, and so it dumps out. So all told, we run it this many times, which is 1, 2, 3, 4, 5, 6, 7, 8 times. What is the difference between I is less than 8 and I is equal to, or less than or equal to 8 in this situation? Would we use one over the other? Okay, so, That is an excellent question. So what you could also do, instead of just I is less than 8, you could do, whoops, you could do instead I is less than or equal to 8, typed on the computer oftentimes as something like this. So I is less than or equal to 8. In this situation, oh, I is less than or equal to 7, no difference. Um, there's no reason to use one or the over the other. I just find I is less than 8 is cleaner to read. Um, But okay, so I'm going to continue this concept though, because this is another thing. So I is less than or equal to 8 would add one more to the loop, because at this point, 8 is equal to 8. So it's still considered true because it's either less than or equal to. The minute we hit 9, though, the loop no longer runs. So the loop 9 is not considered part of the valid values to run the loop on. Anyway, um, that's a nice point to touch on, though. One of the hardest things for people to wrap their minds around when it comes to loops the first time is when a loop is going to run and when it's not going to run. That is to say, this logic of when it starts and when it ends. That tends to be the thing that really kind of messes with people. So that's kind of why I wanted to touch on this as much as I did. So at less than 8, you might think, oh, it's only going to run 7 times, right? However, just like on our arrays, we're starting at 0, which is counted as one of the iterations. So in this case, even though we said stop as soon as I is no longer less than 8, we're actually running the loop 8 times because we started at 0. If we made it I less than 9, the loop would run 9 times. Now, Science is awesome, nice name by the way, made a question, what is the difference between I is less than 8 and I is less than or equal to 7? Why would you use one over the other? Well, the short answer is there's no difference. It's personal preference. Technically, there's a slight difference in the memory that's used, but that all comes down to, at this point, it's negligible because memory, there's so much memory on computers nowadays that it doesn't really matter. So at this point, it comes down to what is easier for you personally to read. For some people, I is less than 8 would be an easier thing to read. For other people, I is less than or equal to 7 would be an easier thing to read because they see here, okay, the equal to 7, all right, cool. So they get into their head that like it's going to run, more than 7 times. For some people, it might be easier to see the 8 there because they go, okay, so it's less than 8, so it's going to run 8 times because it starts at 0, cool, whatever. That's all personal preference. But that is another thing you can do. Now this I is equal to I plus 1, that could be anything. That could be I is equal to I minus 1. It could be I is equal to I times 2. You can mess around with the math in that particular situation, although you wouldn't really want to do that here if I is equal to 0, because then it just would run forever, because 2 times 0 is always 0, and it would never be greater than or equal to 8. But I digress. You can do all sorts of math to this. You could say I is equal to I minus j, and you might have a j somewhere else in your code that's affected by something else. So you can really make your loops sort of dynamic in the number of times they run and stuff like that. You could make the check equal to a variable. You could say I is less than k, and integer I is equal to n. Stuff like that. So you can introduce a whole lot of sort of fuzziness, not really, but fuzziness, so to speak, to how your variables run, or excuse me, your loops run and stuff like that. Now, here's where everything sort of gets tied together. So as long as, let's actually keep this one. So for as long as this loop is true and is running, I is a variable that exists inside of the loop as like a valid variable to use. So we could say like, oh, I don't know, a number is equal to number plus I. And that's completely valid. And the I in this case is going to be the same as this one. So the first time this loop runs, we're going to say number is equal to number plus 0, and then number is equal to number plus 1, and then number is equal to number plus 2, and number is equal to number plus 3, and 4, and 5, and 6, and 7, and 8. Well, not 8, because it ends before it hits 8, right? But 4, 5, 6, and 7, certainly. So we're going to be able to get all of the numbers added together from 1 to 7. So I is a variable that we can mess with. Now you'll notice, since we have so much flexibility over how we start and end for loops, as well as how we iterate them, we can have greater control over how I looks throughout this loop. So I could have had I start at 1 and end when it hits 9. So we could say I is equal to 1 and then I is less than 9, because that would run 8 times, right? And then it'd be a little bit easier for our heads to wrap around. But I didn't. I didn't for a very specific reason, because with arrays, you can reference them by variable as well. So let's put these two concepts together. We can say for int I is equal to 0, and I is less than 8, and in this case, I'm going to say plus plus. Now, I plus plus is a shorthand for add 1 to I. That's all that means. It's just an easier way, because that's one of those little things in programming that you're going to run into a lot, is adding 1 to something. It's referred to as an iterator, because you're going to be adding 1 to something a lot of times in programming, and programmers are lazy, so they wanted a shorthand for it. So I++ was born. That's actually where C++ comes from. C++ is a bit of a pun, because C++ is one better than C. So that's where that comes from. But anyway, so now we've got I is equal to 0, I is less than 8, I++. We'll indent this so it's a part of the loop, and we'll just get rid of the rest of these. Close that out. So now we've got our loop. But what's happening here? So I is equal to 0, right? So the first time this loop runs, LED pins 0. Hey, that's referencing the first part of the array, right? So it's referencing 2. Then we add 1 to I, it becomes 1. LED pins 1 becomes 3. I, 2, 4, 5, or 3, 5, so on and so forth. So what we're doing here is it's known as iterating, but we're going over each element of the array by running it through this loop. Every time the loop increments, it pulls up the next element in the array. And we're feeding it into pin mode and turning it into an output pin. So now, all of that code that we had here beforehand, all of this has been condensed to those 3 lines. We have taken, I don't even know because I don't have line numbers on, but we've taken like 20 lines of code and turned it into about 5 or 6. And we're not even done, because we got this whole monstrosity to deal with down here. So let's go ahead and mess around with this one. So let's get rid of all of this. Boop. And we'll use the same concept. This becomes I, not O, I. And this becomes our for loop again. And I equals 0. I is less than 8. And I plus plus. And we'll throw it inside of our curly brackets and indent it so it's easier for us to read. And there you go. Now our void loop utilizes a for loop and our array in order to condense itself significantly. Now, there might be a couple of questions on your mind right now. Wait, we used I up here. Isn't I equal to 8 down here? Well, first off, I is a variable that only exists for the duration of the for loop. So as soon as the for loop ends, as soon as we move on to the next bit of code, in this case, the void loop, I is promptly forgotten about. It's just dumped out. The computer goes, I don't know what you're talking about. That's an interesting name for a variable. So I is promptly forgotten as soon as the for loop ends. And this happens for both of these. So as soon as this for loop ends, this I is also forgotten. So we go back to the top of the void loop and we start all over again. We recreate I and we start all over again. Secondly, you might be going, why are we using I? Why aren't we using something more descriptive like number of loops or something like that? And you could. We could call it whatever we want to. We don't have to call it I. We could call it P or Z or Q or cat food or revolutions around the sun. Also, we'd probably want to camel case it. We could call it those things. We cannot call it numbers, however. We can't do that, unfortunately, because the computer knows numbers to be numbers. So we unfortunately cannot name variables after numbers. We could say 5. We could type out 5, and that would be perfectly okay. But we cannot use numerals because the computer sitting here is going, okay, I have no idea what you're trying to say because you started out saying, hey, here comes a variable, and then you said 5. That's just a number. And then, as if that wasn't going to make it more confusing, you told me that 5 was equal to 0, and now my brain hurts. So like really what we just did is we just spoke nonsense to the computer because the computer is dumb. So we want to give it this so that it can track. So we can use variable names that are comprised of letters. We can have a number in it. That's okay. So we can say I5, and that's all right because it starts with an I. So the computer knows, hey, okay, so like this is going to be a variable. Everything's cool. This variable just happens to be called I5, and the only reason it knows that is because it starts with a letter, and we got the int in front of it. But we cannot just have a number. It's not going to know. On top of that, it's going to be a huge pain for us to be able to keep track of what's going to be a number and what's going to be a variable if we called it 5. Cannot use symbols. Symbols are not valid. However, you can say pi for pi, and that's okay. Sometimes. The reason I say sometimes is because for some programming languages, though there are reserved words and pi can be reserved. For instance, we cannot name a variable int. We cannot say int because int is a magical special word for the Arduino, and int can only be used in situations where we're trying to declare a new variable. So we can't say int. We cannot have a variable called int because int is what's called a reserved word. A nice rule of thumb is if the word changes color, you can't use it for a variable name. Do not use it for a variable name if it changes color. So you can use letters, you can use words, you cannot use special words, you cannot use just numbers, and there are a couple of other restrictions that you don't really tend to run into, so I'm just going to leave them alone for now. But yeah, those are going to be the restrictions on what you name variables. So you might be saying like I isn't really all that descriptive. You might want to use something that's a little bit more helpful in name. And yeah, you'd be right. Generally, best practice is to name a variable that's something that's descriptive and helpful. However, this is another one of those things where tradition comes into play. Anytime you're using an iterator variable, that's what these are referred to, are iterator variables, for a loop, by convention, it tends to be I. So by naming it I, we can pretty quickly just look at it and go, oh, okay, so that's a variable used to keep track of the number of loops that are happening right now. And if you have like a subloop, so like, because you can nest loops, we can say for int, in this case, we'd use maybe k or j or l or m or n, and then you kind of just run through them. And those single letter variables tend to be iterator names. For other stuff, you tend to want to use more descriptive names, like for instance, LED pins. That's more useful than Okay, what's that? What's M? Why is there an array called M and what does it do? So in those situations, you want to give them more helpful names. In this case, LED pins with a capital P so that you can more easily read the second word. All right, so let's test this out. Whoop. Let's head on over to our Tinkercad. And what you got for us? Control A, Control V, upload and run. Sure enough, runs like a dream, and it's 16 lines of code instead of however much the other one was. I didn't keep track of it, but it was probably something like 30 or 40 lines of code. 30-ish lines of code. So we went from we cut our amount of code well in half, which I feel like should have been more, but we did. That happened. And our code still runs exactly as it did before. And plus, this is kind of like a spirograph kind of a thing. You can mess around with this sort of thing and expand upon the concept. So we can say for int I equals 0, I is less than 8, I plus plus. We can instead say for int I equals 7, I is greater than or equal to 0. In this case, we want to include 0, so I did the greater than or equal to, but I could do I is greater than -1 and I plus plus. And we'll say digital array LED pins I low. So now we've got a loop that turns on all the pins and a loop that turns them all off. And if we run this, and they also run in differing directions, so if we copy and paste this in, boop. All right, we gotta stop running it. Stop simulation. Code editor. Paste that in there. Let's see what happens. We upload and run. They all turn on one at a time. And then they turn off in opposite order. Oh, right, I'm a dingus. What did I do wrong with my code? I have a bug here. Can anybody notice, or can anybody pinpoint it? And in fact, this bug is preventing my code from actually, yep, you got it. This was the mistake right here. If we wanted the loop to go from 7 to 0, we have to make sure to subtract 1 from I. So we've got the equivalent here, which is the decrementer. So, whoops, that's not what I want to do. Copy, paste, upload and run. And now we should see it operating correctly. Up and back down. Boom, look at that. And this is sort of the thing that you can experiment with. Instead of making it up and then down, you could have it start at 0 and have this one start at 1. And you could have I plus equals 2, which is shorthand for I equals I plus 2. And I plus equals 2 here. And then as long as it's less than 9. And you could do all sorts of wacky things. And then you could have you can create patterns by doing this. You could mess around with this stuff. So that's one of those things that you can do with loops is you can sort of mess around with them to get yourself more comfortable with them, because this is a very visual way to see what exactly is going on in a loop. So yeah, you can mess around with that stuff. For now though, I'm going to call this project Dunzo. I wasn't declared in the scope. Aha! So did you throw an int in front of the I? All right. Is your I inside of curly brackets for the for loop? and you named it I. All right, so one of those things, it's either the curly brackets or the int is it needs to be double checked because that's exactly why that's happening. Um, if you still run into a wall, you can copy paste your code into the question box, and I can take a look at it. But yeah, it's definitely going to be one of those two things. So check your curly brackets and check your declarations. If it's highlighting void loop, I would say that it's probably going to be your curly brackets. Regardless, probably going to be your curly brackets. Probably, but you can also one of the things if it says I wasn't declared in the scope, it's probably going to have so for instance, if I do this and I run verify and I hit save, it's going to flip out at me. Yeah, see expected semicolon before delay, and then it highlights that one because it's the problem is actually right here, but it's using its best guess. So it doesn't realize that, well, it kind of does realize that the problem's here, but it doesn't really explain it very well. So it expected a semicolon before delay. Now we know from that message, boom, that should be there. And if we verify it, everything goes through all hunky-dory. Yeah, boom, done. Uh, mm, Depends on the programming language. Let's see if it works for Arduino. I don't think it will, though. Oh yeah, no, it does. Okay. Yeah, white space doesn't matter in the Arduino programming language, just like Java and C and all those languages. So we could actually write all this entire program on one line. So it is possible to put the semicolon on the delay line and have it count as the semicolon for the digital writes, because it'll just get rid of all the white space and it will basically write it as just one long line of code in essence. However, I don't recommend that. I don't think that's a very good idea because then it becomes super hard to read and you're just making your own life harder. And you don't want to make coding too hard. I don't know why I said it like that. I think it was just, I was looking for a silly voice and that came out weird. But anyway, all right, we'll go with it. Yeah, it sounded like the Grinch. Perfect. Um, so yeah, that that pretty much does it for that program. Let's see what we got on the docket for next. And we're probably going to be able to start building the circuit for it, and then we will just uh, do the coding next time around. So let's see here. So yeah, we did multiple LEDs. That was exciting. Super neat. Okay. Pop back over here. Do a little search for Arduino. Lesson 2 and 3 is what we just did. Now we need lesson 4, inputs. Ah, yes. Get ready, because now we're going to start messing around with inputs, which, so far, all we've done are outputs as evidenced by our write commands. Our write commands and our output up here in pin mode. Now we're going to start messing around with things where we'd need to input. Yes, I know, try to contain your enthusiasm. But we're going to be messing around with analog read and digital read, and also serial print. Serial print is going to allow us to view that analog read and digital read a little bit more clearly. Serial print is magical and wonderful. serial print and the serial monitor allow us to sort of view what's going on inside of the Arduino's brain so that we can debug like the Dickens. So let's go ahead and check out analog read first, and let me fix the cable so that you guys stop hearing the thing just sort of bonking the microphone. All right, there we go. So analog read, they don't talk about the difference between analog and digital at all, but we did kind of talk about it. So analog and digital. Analog, well, digital is either on or off, 1 or 0, like we mentioned before. There are only two possible values that digital could ever be. If it's ever not one of those two values, then something is really seriously wrong and physics don't work anymore. It's a little bit dramatic, but certainly for modern computers, they run on one of two possible values, either on or off, for everything on the inside of them, everything. All of the complex stuff that goes on behind the scenes in a computer, everything, all of the that make all the pretty colors on your screen that allow me to yell at you in real time across the nation. All of that's possible because there is an insanely complex array of little switches in your computer, for lack of a better term right now, and all they do is measure whether something's on or off, and there is no in between. And that's it. Your CPU is a set of on and off switches, all just flipping on and off in rapid succession, flipping each other off, on and off in rapid succession. So those are going to be like logic gates and stuff like that. And it's that sequencing of off and on that creates all of the complicated internal logic that computers run. But that's the thing. It's just on or off. They never do anything in between. Now, there's the idea that with quantum computers and stuff like that, quantum CPUs, quantum chips, is that there is an amount of inherent randomness because they could be a value between 0 and 1. So it could, and it's not, a lot of people say like, oh, it could be 2. Like, not technically. It could be like just not 0 and not 1, which is sort of easily explained as 2, but it kind of exists as a value in between 0 and 1. But it's not entirely correct to say that it's like, I don't know, 0.5 or something like that. It's just not 0, but not 1 either. But it could be either one of them, so it's kind of in between. It has a lot to do with when you start learning about like quantum mechanics and stuff like that, which is just stuff that's way over my head, so I'm not really going to get into it. That starts to have it make a lot more sense. So that's the only situation in which you could be not dealing with digital values of 1 or 0. Analog, on the other hand, after that whole thing, analog can have any value in between 1 and 0, including 1 and 0. So you could have 0, you could have 0.3, you could have 0.4, you could have 0.33, you could have 0.9999999, you could have 0.128965543. These are all valid because they exist in the full on and full off. And analog makes that distinction. With digital, you could have voltages running through a circuit that are not just 0 or 1. But with digital, it's got like a threshold. It's going to say, hey, anything below this value, like, it's just going to be off. Anything above this value is just going to be on. We're not going to make a distinction. We're not going to say, hey, okay, so I'm sending you 3.5 volts. I'm just sending you volts. Whereas with analog, we'll go, hey, I'm sending you 3.5 volts. All right, is that, just so you know, that's heading your direction, and it's going to go, oh, okay, 3.5 volts, cool. All right, so I'm measuring 3.5 volts. So analog makes that distinction, whereas digital does not. And that's the difference between the two. So that's what's going to be that's what we're going to start on Tuesday. Is we're going to start out with analog read, and then you're also going to be introduced to the serial monitor, and then we're going to probably on Thursday do digital read, and you'll get to see that stuff as well. And we'll try and sort of combine all these concepts, so you'll see like the potentiometer and the like a push button and stuff like that, and just sort of make it as interesting as possible. Uh, at this point, though, it's 8:47, so I'm not really going to be able to teach you guys any new concepts or really get like a whole lot of progress done with the wiring of the circuit or anything like that. So I'm going to call it a day right now, just to give you guys the capability to leave a little bit early and ask any questions that you've got in case you have any. So that involves me asking the poll questions right now. As soon as the poll questions are done, you guys can ask any questions, or you can head on out. And if you head on out, which I imagine all of you will do at some point here, have a wonderful weekend, and we'll meet up again on Tuesday.